Hello friends, and welcome to the video tutorial series by Elisa. So today we are going to start a new series on a VLSI design. So particularly in this video we are going to cover FPGA architecture. So let's start with this. Before we start, let's have a look at the contents what we are going to see throughout this video. So first of all, we will see why we need programmable logic devices, PLD. Many of us have heard this word. If no, then we can also know this. But we will see why we need PLDs and what are they. What are PLDs? We are going to see PLD because this is the origin from which we move towards the FPGA and CPLD. So why the world actually moved towards these two high-end techniques, FPGA and CPLD, that's also we are going to see. And frequently asked question like what is the main difference between FPGA and CPLD, that also we will see. And then we will move towards the what is FPGA, and we'll start with its architecture, and we are going to cover the FPGA architecture in detail. So this is the contents we are going to go through in our video. Let's start. So first question, why we need PLD? Now to understand this very clearly, let's have a look at the example. Suppose I have an IC, the IC, regular ICs that we have seen many times. Suppose this is the IC and it is manufactured to do a dedicated work. What work this IC does? To understand this, I know that this IC has two input and one output. So to understand its function, I will randomly give any combinations at the input x and y, and I will check its output. And I come to know, as this is the example, I come to know that it gives me the observations like this. This is the truth table for this IC, that is for 00 the output is 0, for 01 the output is 1, and so on. So as you have seen, you might have thinking that this is the truth table for XOR gate. So this is the XOR gate. Wait a minute, this is the IC which function similar to the XOR gate. So don't consider it as a gate for the sake of the convenience. So once I know the truth table, using the K-maps or using the K-map, I can now design or I can write its function in terms of expression, that is A into B bar plus A bar into B. So this is the logical expression depending on which my IC works. So from this I can understand that this IC may have contained two AND gates, one OR gate, two NOT gates arranged in this fashion. Right? Now let's go towards reverse engineering. Suppose in the world you have found a problem, and to solve this problem you have developed your logic, and your logic seems very similar to this truth table, right? So your problem will be solved if you have any IC which works similar to this. So what will you do? You will do the reverse engineering, that from this truth table you will design a logical expression. From the logical expression you will configure, you will map it into two AND gates, one OR gate arranged in this fashion. Now if you want your design to be appeared in IC, you will send this design to the manufacturer, and manufacturer will give you a dedicated IC which will have these AND gates and OR gates arranged in this fashion, right? But let us say that you have now IC, but now you know that I have to change my logic. That is, you have given the solution to a problem, but now your problem is changed or any other thing has been occurred, because of which you have to make change in the truth table. That is, at the input 00, now you want the output as a 1. Of course, this will change the entire design of the IC. So if this type of problem comes in the field when you are working, it is required to change the IC. You have to design it again, you have to send your design again to the manufacturer, and then again you have to wait while the manufacturer gives you IC. So this is the problem when which occurs if we don't use programmable logic devices, because you have the IC which is manufactured and it works dedicatedly on the given function. You are not allowed to make any changes in it. That's why we need PLDs. So PLD use the technology that allows the function to be reprogrammed. But how? Okay, so we will understand this, the programmable property of PLD, by understanding the PLA. PLA stands for the Programmable Logic Array. Actually, this is the type of PLD. We can have a brief look into this. This is the structure of PLA. You can see in the PLA there are 8 AND gates and 3 OR gates, right? And the wires are laid inside it, but one thing is that these wires are not connected with each other. They are just laid in the IC. That's why we can say that this is the programmable AND array. That is, you can program which connection you want to make. Similarly, this OR gates is called as the programmable OR array, right? So you have the 3 input, you have the provision of 3 inputs, right? So suppose I want to execute the same function, that is the XOR gate inside it. So what I will do, I will make the connection between A and one of the input of the AND gate like this. Then B bar, for that I will make the connection between B bar line and the input of AND. Actually this AND is capable of ANDing 6 inputs, but out of which I have configured it to work as a 2 input AND gates by making connections. So output of this will be of course available here, so I will make connection here also, right? Now for A bar into B, I will do the same, that is this A bar line connected with the input and the B, right? And the output of this will be available here. Now these two are configured, so these two will go into the input of this OR gate, and the output will be available at this. So this is the output of XOR gate. Now in between, if I realize that I want to change my design, I can do it by removing this connection and by configuring any connection here, so or anywhere else depending on your design. So in the PLA you can reprogram your design again and again, and how to make this connection comes under different technology that we are going to discuss a bit later, but just understand that you can reprogram them, and the number of times you can program depends on the type of PLA that you use. So this is the beauty of programmable logic devices. Along with the PLA, there is one more technology, PAL, which stands for the Programmable Array Logic. The key difference between them is that PLA has the both AND and OR gates programmable, as we have seen right now, and it has the less number of gates, and PAL have the AND gates programmable but the fixed number of OR gates. That is, you cannot configure the inputs of OR gates, they are already programmed, and you are allowed to change the AND gates only, but it uses large number of gates as compared to PLA. So these are the basic building blocks for the PLD, and these are known as the MSI of programmable logic industry. MSI is the medium scale integration. This word is come because of the number of gates they use. When these technologies were developed, there was the development in the CMOS technology as well. That is, the number of gates that you can put on one IC was tremendously increasing because of the development in the semiconductor industries. So it was possible to put more number of gates in the single IC. That's why they moved towards the VLSI, which stands for very large scale integration, and they changed the structure of PLD to increase the functionality of PLD. Now the developer designed the complex PLDs. The complex PLDs, which is the complex PLD, that is the CPLD, which we all know the word at least. So what is inside CPLD? Now CPLD is actually consist of number of PLDs in it. The PLDs that we have seen was a single PLD, but it contains number of PLDs, and the PLD is programmable, as we have seen, any AND gate or OR gate, but CPLD allows you to connect any two PLDs, any three PLDs, or you can connect each and every PLD of the CPLD with each other. Right, so these are the programmable interconnections. These are used to interconnect these PLDs. So overall the functionality of CPLD is much larger than a single PLA and PAL structure. That's why actually CPLD is used. And the matter of interest is the FPGA. Now you can see the FPGA looks similar to CPLD, but the thing that you have to understand is that FPGA contains input output block. Here you can see, here the pin that you can see on the IC will be there. Now this pin can be configured either as an input or output or a bidirectional pin with the help of this IOB. From this IOB, right? And the second thing it has is the configurable logic block. The logic blocks, these are present here. Actually these are different from the PLDs, but these are the smaller version of PLD, you can say, and the structure of them is entirely different. So in the FPGA they have divided it into so small things that you can merely perform any operation in it. The only limit is your imagination. Like using FPGA you can design any processor or any complex design, right? And the other thing is the programmable interconnect. The wires you can see, these wires are just laid inside the IC. These are not connected. It is up to you which connection you want to make. So from any input pin to any IOB, from IOB to any of the logic block, and from logic block to any other logic blocks, and then to any other IOB. All these connections can be made by you yourself, and this is the beauty of FPGA, which is by the programmable interconnect. We are going to see all of these three in detail, but by now you all might have conquered with a question that how actually a programming is done to FPGA. Like we say that user can configure everything inside it, but how to do that? Well, there are many vendors, giant vendors we can say, available in the market, some like Xilinx, Altera and Actel. What these vendors do, they actually manufacture the FPGA ICs as well. Also they gives you a software along with it. Yes, the software along with it. So as we say that FPGA is as simple as any programming language. You can configure any configuration logic block, any IOB or any programmable interconnect by writing it in particular language. These language are nothing but the hardware description language. Hardware description language like VHDL and Verilog. If we talk about the Xilinx provides you the IAC software, Xilinx 14.2 or 13.2 you might have known. In this software you can write your logic using the hardware description language like Verilog and VHDL. You compile it, you synthesize it actually, and from that you build a bit file. This bit file itself is generated by the softwares provided by the Xilinx. So now this bit file contains all the information about the programming inside the CLB, which CLBs to be connected, what logic you want to actually do it in the FPGA. All these things are available in the bit file, and you can upload this bit file into the FPGA kit just like you do for any microcontroller kit. You write program in C language, you compile it and form a hex file, and you then dump them into the your microcontroller kit. The similar action happens in the FPGA. You write your program, but in the hardware description language, the syntax and everything are different from the C language, and Verilog is much similar to the C language. And you can compile them, generate a bit file and dump into the FPGA. So this is how FPGA is programmed. That's why most of the time it is said that FPGA are as simple as the any software or any programming language, right? And the other comment that I would like to make is that FPGA uses SRAM based programming. Now you might have seen that there are two wires, and I often say that if you want to make the connection you can make, and if you don't want then leave it. This is a statement I have used many times throughout this video. So we will see how this is made. Now you can see that there are two lines laid over here, and these lines are not connected with each other. Instead they have provided a block U. Now this block, depending upon this block, you can say FPGA uses SRAM based programming, because inside this block you have one MOSFET and one SRAM cell. SRAM stands for Static Random Access Memory Cell. You all might know that MOSFET conducts when 1 is written at its input, and it won't conduct if 0 is connected at its gate, right? So in the FPGA there is a SRAM. In the SRAM, if you write 1 at this particular cell, then the connection will be made. That is, these two lines will now have a physical connection through this MOSFET. Okay, and at the moment you write the SRAM cell with 0, this connection will be now disconnected. That is, you can program it to be connected or disconnected, and the technology which is used to do so is the SRAM based programming, which is used in the FPGA. Actually in the CPLD a floating point gate method is used. You can search about it, but I would like to say that there is no memory inside the CPLD to program the connections, but FPGA uses the memories. So what problem is with FPGA is that SRAM are volatile. We know that using SRAM we can reprogram it, and these are of read or write type, so you can know the status of two lines as well as whatever you write, these lines may make connection or disconnect. But the problem is that they are volatile. What is mean by volatile? That suppose there are 3 to 4 connections that you have made by writing the 1 in the SRAM cell, but when you switch off the power to FPGA, the content stored in the SRAM cell will be vanished. This is what we call as the volatile, because of which when you start the power to FPGA, it won't retain its previous state. And if you want the previous state to be retained, you require an external PROM, which is the non-volatile memory, uh, that is the read-only memory, programmable read-only memory, which is the non-volatile memory, that it stores the data in it even after the power has been switched off. So whenever you power your FPGA again, this PROM will program the SRAM cells, and these SRAM cells will now make the connection between the two wires. So this is the SRAM based programming that FPGA used, and this makes it different from the CPLD. So the basic difference in the CPLD and FPGA is the programming that they use, right? So now we move forward. We are going to concentrate on the Xilinx FPGAs, because at the student level the Xilinx offers you many FPGA kits which are programmable and have many features. But along with the Xilinx, you will come to know two words: the Spartan Xilinx kit and the Vertex Xilinx kit. Actually, there are many difference between these two versions of the Xilinx FPGA. The first is that the Spartan kits have the gates in terms of kilo, while Vertex has the gates in millions. So Vertex has the more gates, but Spartan works on the low power, and the speed concerns are also there. So you can search about the particular kit in the Spartan and the Vertex version, and you will come to know about its difference more easily. Most of the time at the student level, the Spartan kits are preferred, right? So today, to understand the FPGA architecture, we are going to take Xilinx XC4000 family as our reference to understand FPGA. I actually downloaded the PDF file, the datasheet provided by the Xilinx. You can also download it. It gives you a detailed information. So the first block in the FPGA is the configurable logic block. Let's look at them. So the CLB in the FPGA actually contains two slices. So this is the entire CLB. Now inside the CLB there are two slices, slice 0 and slice 1. These two slices are actually identical to each other, and the circuitry inside these slices are same. With the help of switch matrix, you can select any one of the slice. Also, there is provision to make connection between these two slices, right? So this is the CLB, which has the two slices, and each slice of CLB will have four independent inputs: function generator F and G, three fully independent or partially independent input function generator H, D flip-flop, and the routing multiplexers. So we will see all of these three with the help of the diagram. So you just need to understand that in the CLB there are two function generators F and G, which has the four inputs. There is one function generator H, which has the three inputs, and there are the D flip-flops working as a storing purpose, and there are multiple multiplexers which are used for the routing. So here is the CLB diagram. It looks bit complicated, but if we analyze each and every term, it will be very easy. So first of all, let me tell you that these sign are the multiplexers. All of these you can see here. These are the multiplexers. These two are the D flip-flops, and this is the H function generator, and this is the F and G function generators. Now starting from the function generator, we have said that there are two function generators with four inputs, G1 to G4 and F1 to F4. Also we have said that these are independent. Why? Because from the external circuitry out of the FPGA kit, you can have any input and route it through your input output block, and that can appear in the at the input of the function generator. Okay, like here. So this function generator is able to perform any function. For example, if you want the 4 input AND gate, this function generator will work as AND gate and provide you the output like that. If you want this to be work as a NAND gate or XOR gate or any of the gate, this function generator will do that and give you the output accordingly. Even if you want that these four inputs should be come inside the function generator, and function generator should perform the addition on it and give me the output, that is, it should work as a full adder, a full subtractor, or you can say anything like that. The function generator is capable of doing that. So what circuitry will be there inside the function generator that it performs any of the logic function that I need? This is the question that we are going to see a bit later, but for now you understand that the function generator can perform any operation and their outputs are available at G dash and F dash. Right. Now we will move towards one more function generator, H. This function generator has the 3 inputs. Now we have said that this is partially independent or fully independent. Why so? You can see the two inputs of the H function generator. There is the mux, and this mux has one of the input as the G dash. That is, the input of this function generator may depend on the output of this function generator G. That's why it is partially independent. But there is also a provision that you can make it fully independent, because here are the C1 to C4 lines. Now these lines are independently coming from your input output block or from any other CLB, right? And these are available here. And with the help of these mux, you are choosing one of them which is available at the input of the function generator H. Okay, and also the other C1 to C4 lines selected by these two multiplexers are actually coming. You can select them using these mux and can appear here also. So this H function generator is also similar type of a function generator as same as the F and G, and give you the output H dash. This function generator performs merely any operations. Okay, now the output of H dash along with G dash is available here. These G dash, F dash, H dash are available in these mux. You can see these 3 muxes, actually the 4 mux, this H dash, F dash, D in, F dash, G dash, H dash, and the so on. Output of these function generators are available now here and here. By selecting one of them, you can directly make it visible at the output Y or at the output X from the function generators here, from the mux here, or you can give it to the output pin by passing it through a D flip-flop. Why D flip-flop? In case you want to store them and you want the output only when a particular clock applies or after some time, for that purposes you can store it, the output, at one of the D input of the D flip-flop, and whenever you need you can provide a clock. You can provide the clock coming from the here, and you can make it available right here, or you can also bypass it from the D flip-flop, right? And the clock generator is here. This is the clock line. So and these are also the set and reset circuit. This is the enable clock circuit. You can select any clock, any set reset pulse. All is possible with the help of this multiplexer. So this is the structure of the CLB, the function generators, the routing multiplexers, the D flip-flops, and the multiplexers, right? So now we move. Now as I ask you, what is inside the function generator that makes it able to perform actually any function that it wants to? So the answer is that this function generator are nothing but the lookup table. What is lookup table? You can consider it as a truth table also. We will take the example of the same XOR gate that we choose, that I want a function to be operated like this. So what a function generator does is that it converts the function in the truth table. With the help of the hardware description language like Verilog and VHDL, you have given all the information about your gate, that is that it is the two input gate, it will have one output, and when the 0 0 is applied, the output will be 0. When the 0 1 will be applied, the output will be 1. These all information actually you have provided by writing it in the code language, that is in Verilog or VHDL. So FPGA will know that there are two inputs, right? So because of that, it will have all the possible 4 input combinations and their corresponding output. These all will be stored in the memory. Yes, in the memory, the outputs will be stored as 0, 1, 1 and 0, and those memory locations will be accessed by your inputs. So if the input is 0 0, a memory location will be read, and in that memory location 0 will be stored. So if input comes as 1 0, then the memory location will be read where this bit 1 is stored, right? So FPGA actually uses the lookup table instead of the actual hardware implemented inside it. The advantage of it is that whatever may be the complex function that you want to execute, the time required for that will be same for AND gate also, or for any adder circuit. The time required to execute that function will be same, and it will be equal to the time required by FPGA to read the particular memory location. Okay, so you will have a memory like this, and the bits will be stored, and these bits will be accessed depending on the input. So if it is a complex function, also for the complex function you will have the truth table like this, and this will be stored inside the memory. And in the memory, whenever the input comes, this function generator has to read those particular memory location, so the time required will be same. That's why FPGA works bit faster than any other, because the implementation inside them is the lookup table, not the actual gates. But if you want to make it feel like the real gates, then you can add extra delays to it. Okay, so this is how the function generator works. Now the next thing is the input output block. The input output block provides the interface between the package pins and the CLBs. Each input output block can work as unidirectional or bidirectional input output. The outputs can be forced to high impedance. Inputs can be delayed. These are the features of the input output block. So we will understand this by its diagram, its block diagram. So this is the detailed diagram of the input output block. Okay, so in this diagram again you can see there are the D flip-flops and some of the mugs. So let's start analyzing it. We will start from here. This is the pin pad. This pin is available outside the FPGA IC. This is the physical pin that you can see, right? So suppose you have configured this pin number as input, and you can do this in the Verilog or VHDL. The syntax are available there. Okay, so if you configure it as an input, now this will go and follow this path from the input buffer your input will be available here. Now from here it can either go in this direction or either go in this direction. Why two paths? First of all, we will see that if the input is available, so it will be directly available at the input of this mux, and this mux will choose one of these inputs, and it will be available in the I1. From I1 it can move to any of the CLB. But as I said that FPGA works at very high speed, right? So it is always necessary that the external circuitry is synchronized with it, and in order to synchronize you have to pay attention at the instances when the input will come inside the FPGA, the instances at which the output will go outside the FPGA. For that purpose you always need to add delays. The provision is provided here, that is the input is now available, but now this input is delayed by some nanosecond or any seconds depending upon your requirement, and after delaying it you can store it, and whenever you need you can make it available in the input. So this provision is provided in the FPGA, right? So in the that's why the delay function is used. So flip-flop directly available or from any delay, and the clock and the clock enable are also can be also programmed inside the FPGA and can be given to the D flip-flops. So this is the part, that is the lower half for the input. Now consider this is configured as a output. So whatever output will be come from inside the FPGA at this pin out, right? And this out pin can be negated using NOT gate and available at the output of this mux. You can choose this directly and made available at the output, or you can make it available through D flip-flop. The clock enable is same as this one. This clock is different because you may need the output at any different instance, right? And this is the pull up pull down logic. Suppose this pin is not used, then you can configure it to be low for all the time by the pull down resistor, or you can make it high all the time by using pull up resistor. So this is the functionality of input output block IOB of the FPGA. So now we move towards the programmable interconnect. Well, this is the best which we have saved for the last, because the programmable interconnect is actually the beauty of FPGA. This architecture is fascinating example of a structure that provides rich, symmetric connectivity in small silicon chip. We are using the word that the FPGA is configurable, the FPGA is programmable. All this programmability is achieved with the help of the programmable interconnect. Each CLB in FPGA is embedded in the interconnect structure, which is really just wires with programmable connections to them. Okay, so we understand this by diagram also. So inside FPGA we know there are many number of CLB, but these CLBs are also surrounded by this many number of the wires. As you can see, this is the one block actually, right? Now this is the block which is repeated million times inside the FPGA kit, and this makes it to work at very high speed and merely any function you can observe. So from the CLB there are two output lines which are mentioned as the direct connect, right? So from these CLBs, this output can directly go at the input of any other CLB, because this same array will be here here. So these CLBs can directly connect to any of the CLB which are connected to the bottom, on the right, on the left, or on the top of this. So these four lines are now made clear. Now you might have seen that all these lines are assigned with a word and a number is written inside it. What are those? Actually, these are the group of the wires. This is the group which contains 3 wires. This is the group which contains 4 wires. This is the group that contains 8 wires, and this is the group which contains 12 wires. So they are named as long, double, single and quad. Okay, and these are the bidirectional, that is three wires inside this group. One can move in right direction, other two can move in the left direction anyhow. One of them is the global clock, which connects 4 wires. You have seen in the input output block the clock enable, the clock signal that goes to the D flip-flops are actually the wires that go into the global block. So suppose you have assigned 3 CLBs to work simultaneously, and the output of these 3 CLB is your actual output, right? So it is required that you provide the same clock to all of these blocks. That's why these global clock are used, and other are there to route the data signals from one CLB to other and so on. So you might be thinking that why these groups are made. Only one group of say 15 or 20 wires can be done. There is also a reason for this. The reason is that in the FPGA the CLBs are placed at different places like this, and they are surrounded by the group of wires as we saw in the in our previous slide. Okay, so suppose this CLB is to be connected with this CLB, so there must be a wire routed from this CLB to this one. So it is not possible to have a wire already laid between these two, right? That's why at many instances PSMs are provided. What are these PSM? PSM are the programmable switch matrix. Okay, this switch matrix will actually route one of the wire in this direction. This PSM will route the wire in this direction, and it will go inside this CLB. So this CLB. So of course, if the routing is done through this matrix, then some delay is added to it. That's why the 3 categories are done: single, double and long. The single are the wires that go into the PSM every time. That is, if I want to move from one CLB to other using single, then the CLB will provide its output to its single wire. This single wire will go into the PSM, will get routed and will go into this CLB. So every time single wants to run from one CLB to any other, it has to pass through this switch matrix, which adds the delay. So in a function you require that I don't want to add any of the delay, then you can use the doubles, because doubles actually connects 2 CLBs without going into the PSM. They can be directly connected between 2 CLBs. So a delay between these will be very less or nearly zero, because the connections are directly made. That's why we use the double. And one more type is the long, which is not shown in this figure, but this long can travel at a longer distance. You can see in this figure, the long can travel for the longer distance passing the CLBs without going into the programmable switch matrices. So now we have to also understand what is programmable switch matrix. So PSM actually contains all the wires in it, and it has this type of nodes. Now these nodes are zoomed out and are possible here. So you can say that this is the different wire on the right, on the left there is different wire, below and on the top all are the different wires. Now these two wires, if I want to connect the right wire to left wire, I will have the connection between these, like along this dotted line, right? So I am routing this here. If I want this wire to be connected here, I can route it in this fashion. From this dotted line you can see slant line. Okay, if I want these 3 wires to be connected, then I will connect this bottom along the vertical dotted line, and this vertical dotted line connected to the half horizontal dotted line. So this programmable switch matrix can route any CLB to any other CLB with some delay. So this is about the programmable interconnect, and by this we actually complete the FPGA architecture. So if you have any doubts regarding the FPGA, please do comment, and if you like my video, then you can subscribe to our channel and also like us on the Facebook. VLSI are making many more useful videos. You can have the links in the description, and thank you for watching it. Thank you.